the new stuff. Where are we? I'm gonna start right here. Standard error of the proportion this week. The only difference between this week and the week we just handed in the homework for, just finished, is the word, the proportion, instead of the mean. This is the first time you've seen this denominator. This denominator is very different, but it's just like standard error of the mean, except it's using proportion. This is the first time you're gonna see problems that you calculate z and use the normal distribution equations, but there's no standard deviation. Matter of fact, I thought to myself, I want to show you an example problem, homework problem, but in this case, what number was it? 23C. All right, let me see if I can make this bigger. Okay, here's an example of a proportion question that you got to recognize you're using z even though there's no standard deviation. 23 says, a random sample size of 200 is taken from a population with the population proportion equal to 0.75, 75%, there it is. C, what's the probability the sample proportion is less than 70%? No standard deviation was given. But it was talking about a proportion and asking about a proportion. It gave you an expected or given proportion, and then it asked you about a proportion. And it also included a sample size. Those are the three numbers in the formula. The proportion being asked the probability of is the first one, just like with the mean, is the number you're being asked to find the probability of. It's the proportion you're being asked to find the probability of. Minus the proportion given or expected. So in this case, you look at 23, hey, the population proportion is 0.75. That's the given expected one. That's the one on the right. And then the question, what's the probability the sample proportion is 70%? That's the one you're being asked the probability of. That's the one on the left. Now here's where many mistakes get made. The two proportions you use in the denominator are the expected given proportion, not the one you're being asked about. The one on the right, not the one on the left. Those are also used in the denominator. The given or expected proportion that you put on the right in the numerator is the one you're using in the denominator. So in this case, the 0.75, which is given, is also right here, 0.75, times 1 minus 0.75. So this is 1 minus 75% is 25%, times 75%, the given proportion. Divided by the sample size. In this case, it's 100, I think. Is that what it was? No. 200. Excuse me. Divided by 200. Then the whole thing is square rooted. When I say the whole thing, the whole denominator is square rooted. Again, here's the number 2 mistake that takes place. Don't just square root the top part of this denominator. That square root needs to come all the way down, showing you're square rooting the whole thing. The whole thing in the denominator. That square rooted portion, and the square root, is what's called the standard error of the proportion. This is what's new this week. Other than that, everything's the same as last week. Your homework's the same. Look at these problems. I want to show you the problems on your homework. First of all, where's our instructions? Oops. We have, let's see, today is our lecture, and we have Thursday, which is the recording, no face-to-face Thursday, don't forget that. We're learning today's lecture. There's one of our most important items we're learning today. Central limit theorem. There it is. Central limit theorem. I can't ask you to highlight these words enough on your notes right now. Central limit theorem. There is a 99.999.99, there's not another point, but 99.9999999% chance this is on your final exam. Central limit theorem. Without a doubt. Anyway, homework is due a week from today, which is April 9th. There's only one assignment called the written Excel assignment. It's going to look a lot like the assignment you just handed in today. Let's take a look at it. It's got 1A, 1B. Okay, here's the big difference, highlighted. Here's one big difference this week. Leave at least 5 digits to the right of the decimal for this assignment. You're using 5 digits to the right of the decimal. 5 digits to the right for this assignment. because there's so many leading zeros on a couple of these, or at least one for sure, that you hardly get any numbers at all if you only go 4 digits. You get one number maybe. So I need you to go 5 digits on this assignment. And if you have, and don't forget, we've been going 4 digits to the right all semester, and it's 4 digits to the right on the final exam, unless the instruction of the top, right above the problem or right during the problem mentions to go 5 digits. That'd be the only reason you have to go 5 digits, it's if the instructions say so, which is the case on this homework. So 5 digits to the right, but you're doing the same thing. Manually calculate your z-score using this equation right here. Then use norm S distribution or 1 minus norm S distribution and your result. These are your part A's. And how many of these do you have? I think you have 5. Not 8, but 5. 1, 2, 3, 4, 5. Tell me there's one between 2 numbers. I forgot. Yeah. 5 is between 2 proportions, just like being between 2 numbers. Between 2 proportions. That's in Thursday's lecture, a demo of how to do between 2 proportions. But you can imagine, there's no difference between this week than last week, except we're using proportions instead of mean. And when you did it between 2 means, you treated it like 2 separate problems. You manually calculate a z for one, you manually calculate a z for the other. That's what you're doing again this week for number 5. Manually calculate the z for one of the proportions, manually calculate a z for the other proportion, plug them both into norm S distribution, either as one equation or 2 norm S distribution equations, and then subtract. Or the one equation subtracts. No different. This week, if you thought last week's homework, you guys said it twice, that last week's homework was easy, the one you just handed in, that means this one's gonna be easy. Because this is the only part that's different, just this little denominator. That's it. Matter of fact, I've already, in this, remember I said I had a meeting Thursday? In the meeting Thursday, we're talking about adding some more business analytics to statistics. And I'm already thinking in order to get some more business analytics involved in statistics. Business analytics is, using numbers to make decisions. Remember this, a tool that would be similar to business analytics would be that simulation I showed you a couple times. That'd be kind of similar to using business analytics. But I'm gonna take this week's homework assignment and shorten up last week's homework assignment and make these 2 all just 1 week. That's how easy this week is and last week is, in my opinion. That they could be done in 1 week. That would free up a week then for some business analytics to add in. So anyway, that's how easy this week is. Just so you know. So there's what the questions look like. Again, each A is asking you to do this manually and then use norm S distribution. And then each B is asking you to use normal dot distribution without the S. Give the whole equation. Here's in words what the numbers are, because it's slightly different than last week. The proportion being asked is the first number, just like the number being asked was the first number with the mean. Now with the mean, the second number is the given mean, but this one is the given proportion, the expected proportion is the second number. The third number is the standard error of the proportion. And I'm putting it in words for you because this is the way to do it. If you don't do it like this, you need to show this math, whatever this calculates out to. If you're going to use the number, you got to show it on the side as to what this calculated out to. But I'm suggesting to avoid the rounding and put this in exactly as I'm putting in words here. SQRT, parenthesis, the proportion expected, you got to use an asterisk, parenthesis, 1 minus the proportion expected, parenthesis, divided by sample size, parenthesis, comma, 1, parenthesis. Yes?
For the equation right there, is it probably expected divided by given?
No, not divided by given. Hang on, let me put a dash. It's just another word for expected.
Oh.
Expected or expected. If I use a dash, you'll think I'm subtracting. So I don't know what to put here. How about if I just put
Expected given. Oh yeah.
How's that? Is that better?
Yeah.
I don't know if that helps either. Could be
I thought it
multiplied.
was divided.
All right, so I'm just using, I think your book uses the word expected, and I used to always use the word given, so I'm trying to use both words. That's all. Okay, so we know what the A's are, we know what the B's are. There's only 5 of them. Let's go into, before I go into an example, I have the stuff to prepare you for some multiple choice questions. Sample bias, selection sample, using selection bias as part of sampling, non-response bias as part of sampling. These are all ways to screw up a research project. Is this kind of sampling we're going to talk about. I'm going to define these a little more. Simple random sampling is one form of sampling. Stratified sampling is another one, which has greater precision. That would be the advantage you want to write down about stratified sampling. We'll talk about that in a minute. Cluster sampling is another form of sampling. Less expensive would be the biggest advantage of that one right there. Central limit theorem I talked about already. And then Excel, we have z-test to learn. Z-T-E-S-T, that function right there. What about, I want to mention over here. Hang on, what is this? I already talked about those. 89 minutes, talk about that, that's it. All right, let's get into the boring stuff. Okay, I want you to notice there's 2 Chapter 7 PowerPoints now. This is Chapter 7 PowerPoint B. So there's Chapter 7 PowerPoint and B. We're now on the B one for the first time. Here I want to just mention the definition of bias. Sample bias, the tendency of a sample statistic to systematically over or underestimate the population parameter. I'm going to mention the central limit theorem now. The whole point of doing sampling is to be able to learn something about the population, called inference. We can infer what we're learning about the sample towards the population, but it's all about you being able to do the sampling correctly. If the sampling is the key to infer, to have correct inference, I guess, towards the population. That whole thing is called the central limit theorem. This is why it works. But the central limit theorem has a couple of rules, and here they are. One is, if you're talking about a mean, remember, like a standard error of the mean type problem? The sample size has to be greater than or equal to 30. That's kind of the rule for the central limit theorem to work when we're talking about a mean. The rule's a little weird when we're talking about proportions though. Proportions, you gotta take the sample size times the expected or given proportion and see if that's greater than or equal to 5. And you also got to take the sample size times 1 minus the opposite of the expected or given proportion and make sure that's greater than or equal to 5. Both of these have to be true at the same time for the central limit theorem to work. That's the rule. And then when you, and if you truly use one of these sampling methods the right way, again, giving all those in the population kind of an even chance depending on which method you're using, what that means, then the central limit theorem works. These rules and your sampling. And what you find out about that sample, especially if you do a couple of samples, you are going to learn some significant information about the population, and you can infer some things about the population because of the central limit theorem. That works. All right, so bias though. Here are some of the problems that researchers come into where they don't understand how important sampling is. And so they create bias. And so they end up falsely making statements from a sample about the population that end up being false because of a mistake they made when it comes to sampling. And that's called bias. So let's look at this one. This is back in 1936. This literary digest, which I think is out of Chicago. Does it say that on there? I don't know if it says this. They went ahead and during the presidential election predicted, it put on the front page, a landslide victory for Elf Landon as a loss to Franklin D. Roosevelt. So we all know that that was wrong, that was a false assumption they made. So then after this happened, they said, okay, why? How did this happen? How could you dedicate the front page of our newspaper with information that ended up not being correct? And they said, oh, we did a sampling. Let's see, they were wrong. FDR won in the landslide. They committed what's called selection bias by randomly selecting their own subscriber membership list. They didn't call outside those who happened to subscribe to their particular literary digest, if that's a newspaper or a magazine or whatever that is. They only called those. All of those people could be all maybe within the same political party, or they could have all been for the same president. All the voters who voted for president in the United States happen to be on their subscription list. So they canceled out a whole bunch of possible people that are in the population voting, but are not part of their subscription list. That's called selection bias. And that's why they got the wrong results. That's one of the reasons. They also committed a second bias. In addition, only 24% of those who received the questionnaire, who you're voting for president, responded back. So that means there were, 76% said, I'm not gonna answer this. And I'm not gonna send it back to them. It was probably done by mail back in the 1920s, or 1936, excuse me. And so that's called non-response bias. Meaning, back then, now we can call somebody and catch them off guard. Don't get me wrong, I never answer my phone, but you guys probably still answer your phone. You're not old enough to be wise enough to answer your phone yet. But they call people and go, hey, we're doing this survey. All we want to ask you is one question: who you're voting for president? And most people will probably answer. But they're calling. They have phone numbers from people all over the United States, not just from one that read one newspaper only. And only calling from that list, and then not being able to call them and send them letters and only getting 24 response who felt it was important enough to let them know who they're voting for. That's non-response bias. So there's two different biases right there. Here's the definitions. Selection bias, they systematically underrepresented a bunch of groups of people because they only were sampling from their own subscription list. Non-response bias, there's the other mistake, because they went ahead and relied on those to voluntarily respond, instead of pushing the issue some way or another like they do on the phone sometimes. All right, so we got those. Now, where am I going? Simple, defining simple random sample. This is exactly like we've been talking about all semester. I'm gonna bring it up a couple times today, but you remember we're a director of admissions. We have all these applications here. We've accepted 900 students. We haven't got all their information into the system yet, but we have a pile of 900 applications here. We numbered them from 1 to 900 and we picked 30 at random. Remember that whole story? Well, that's the technique we use because it was a finite population, meaning it can't get any bigger. It was 900. That's called simple random sampling. Every one of them had a chance to be one of the 30 with the process we used because we numbered them all. So there's that definition for simple random sampling. It's the most common used sampling method when it can be used. But sometimes populations are too large to be able to use simple random sampling. We can't number them all. So we go to, hang on a minute, stratified random sampling. Stratified is where you break the population into subgroups called stratas. And the most common subgroups I'm familiar with is breaking them up into age groups. Everybody's in their 20s, everybody's in their 30s, everybody's in their 40s. So then, what's nice about stratified random sampling is once you break the population up into groups, you can then get data before you do your sampling of what percent of the population belongs in each group. For example, let's say the population's everybody who lives in the continental US, or all 50 states even. And we decide to break the population up into subgroups by age. Number one is every subgroup has to be mutually exclusive, meaning no one from the population can belong to any more than one group. So if we do age, let's say the 20s, people in the 30s, people in the 40s, nobody can be both in their 30s and 40s at the same time when we do this. They either can be in one or the other. So each group has to be mutually exclusive, where everyone in the population can only belong to one group or another. So that's how you break them up into groups. Then you get information about the whole population as to what percent each subgroup is in the population. Here's the example. I said every person in the United States. Well, we can get statistics from the US government as to what percent of the population is in their 60s. And then we want to then have, let's say we're going to have a sample of 100. And let's say 20% of the population's in their 60s. Let's say 10% even is in their 60s. That means we want to have 10% of our sample be in their 60s. That's what stratified sampling is all about. That's why it's more precise. And let me repeat that. Let me use people in their 20s. Let's say 25% of our population is in their 20s. You want to mirror that in our sample. So you want 25% of our sample to be in their 20s. So since our sample size is 100, you're going to sample 25 people in their 20s, so that you have 25% of our sample in their 20s. You get it? You try to mirror the population subgroup percentages in your sample. And that's what makes our sample so precise, is because you're mirroring what the population represents of the subgroups. They do this with ethnicity also. They do it with, they could do it with males, females, but that's only 2 subgroups. All kinds of other subgroups, and then they look at, okay, let's look at the population. It's just residents of Michigan. Okay, how many people in Michigan, what percent of Michigan residents are in their 30s? Okay, now our sample needs to have that same percent in their 30s in our sample. That's why it's so precise. So there's another form of sampling other than simple random sampling called stratified random sampling. One more I'm teaching you, cluster random sampling, cluster sampling. This one is also kind of breaking them up in group called clusters. The most familiar cluster sampling technique I'm familiar with is geographical clusters. Again, each cluster has to be mutually exclusive, meaning any object in the population can't be in more than one cluster. So, for example, let's say we're doing residents of Michigan, and we decide to use clusters of county lines. Notice, there's no way a Michigan resident lives in 2 counties at the same time. They're either in one county or the other. So we have Oakland County, Wayne County, Macomb County, Livingston County, Genesee County. All these counties would be our clusters. And then we would sample from our clusters, each cluster. Maybe we'll go with, hey, we're gonna go ahead and we have, I don't know, 20 counties. We're gonna get maybe a little more from one county than another because they have a bigger population, but mainly we're gonna just randomly sample from each county then a certain amount, and we're gonna have every county represented in the overall sample. And that way you have a broad sample that represents everybody. So that's called cluster sampling. Does everybody tell the difference between stratified and cluster? Stratified's more, you're breaking it into something that has to do with each person, like age or ethnicity, but cluster has nothing to do with the person other than where they live, for example. Right? And they're breaking the groups. Could be blocks. We're gonna sample from this block and that block and that block, and we're only taking 4 from each block, so every block's represented then in our sample. All right, is that it for the definitions? Let me look at my list, is that it? Don't forget the important parts, the advantages, nice multiple choice questions as to the advantages. I'll repeat these. Stratified sampling, the biggest advantage is greater precision, meaning it really hones in on matching the population more. And then the advantage of cluster sampling is less expensive. That's the huge advantage of that one. Okay, before we get more into central limit theorem, I do want to talk about that. I want to jump to Excel z-test. By the way, anybody that came in late, don't leave without me handing back the stuff I have to hand back to you, all right? All right, so z-test is a new Excel function we're gonna learn right now. Z-test basically does everything that norm distribution does for you, but instead of you knowing all these numbers, you just have raw data. It does everything this does, but you have raw data because you don't have all the numbers. You don't know this, you don't know that, whatever. So here's the example right here. Let's say we found the mean. The mean of this data right here, B8 through B15, is 1.3875. So what's the probability of in the data, what's the probability we randomly select a piece of data out of there and that it ends up being less than 1.3875, the mean? Well, there it is, 50%. Because 50% chance of the mean, 50% chance of the mean, right? The mean's always in the center of the bell curve. Now here's another one. What's the probability that observation of this data will be less than 1.45? Equals z-test, B8 B15, comma, 1.45. So you're putting the range of all the data, comma, and whatever it is you're trying to find the probability of. Now what if this said more than 1.45? All you do is put a 1 minus in front of the z-test. Just put a 1 minus in front, and here it is. Equals 1 minus z-test, parentheses, B8 B15, comma, 1.45. Now, here's how we used to do it. I went ahead and put the long equation. Here it is before today. Equals norm dot distribution, 1.45, comma. We don't know the mean of this data, so I put an equation in my norm distribution. Average, parenthesis, B8 dot dot B15, comma. We don't know the standard deviation of this data, so I put STDEV, parenthesis, B8 dot dot B15, parenthesis, divided by square root of count, CONT, parenthesis, B8 through B15. It's telling me how many pieces of data are in this sample. And then I had to square root the sample size and divide it into standard deviation. I had to use all words because none of these numbers were given to us, just the raw data. Comma 1. So as you can see, I took this whole norm dot distribution equation with equations inside the equation to use with raw data and made it into one. You can break it all down to one word. And there it is, same thing. Equals z-test, parenthesis, B8 through B15, comma, 1.45. We want to find the probability of 1.45 or less. So this is a great shortcut.
This is not on Canvas.
This is on Canvas. Yep. What do you mean it's not there?
It's not there.
Go to week 12.
Yeah, it's not there.
Does it say Excel z-test example?
No.
What? You're on week 12? You sure? All right. Will you send me an email real quick and tell me to put it there? Thank you.
Do we even need it?
Yeah, what do you mean we need it? I just taught it. But election night, you need it. What do you think the odds are that this will be on your final exam?
You have it on week 11.
What'd you say?
I found it's on week 11 now.
I put this on week 11 by accident. Because last year I fit it into
Oh,
week
I see
11.
now. It is on week 11.
Okay, I need to get it on week 12 also then. Go ahead.
Is after the 1 minus probability expected, is that on the top? Is that a division sign or a parentheses?
Where are we at?
Towards the end where it says sample size?
That is divide.
Okay,
That's definitely divide.
okay.
Yeah. You guys see that too?
Mm-hmm.
That's definitely divide there. I'm doing the whole denominator all in words right here. The proportion expected, you gotta put an asterisk over there, 1 minus the proportion expected, divided by the sample size, and then I have parentheses around the whole thing with SQRT in front.
Did you say for or more would be 1 minus?
You can put a 1 minus here, watch. You ready? This is gonna be 1.145 or more. Boom. Equals 1 minus z-test, B8 dot dot B15, comma, 1.45. So you can do a 1 minus in front, just like any of the other ones. So we got z-test down now, right? We're gonna go back. We're going back. You know what? We're gonna do a quick example. Here we are. Here it is. This is, again, you're the director of the admissions. You have 900 applications we've accepted. We haven't got them in the system. Remember going to that meeting, you were being asked what percent said, yes, I want to live in the dorm. Well, that percentage you're being asked about is a proportion. Is a proportion. And we reported, let me try to remember here, hang on, is this it? No, that's the whole thing. Here we go, we did a sample of 30, here they are. Yes, yes, no, yes, we counted how many, and even though the math is off, ignore that. And 20 whatever, out of 30-ish, around 0.68, should be 0.67, ignore that. 0.68, so 68% is what our sample came up with. Well, here's the deal. We then did the whole population. We got them all into the system. And look really what it was. 648 out of 900 say yes. So we reported at the meeting 0.68, but it was really 0.72. They're pretty close to each other. They're pretty close to each other. But here's the deal. What could we have reported by accident that would have been a disaster for the housing director? Like if we reported something too low, like 0.95 or less, that's what we could calculate. That would be a final exam question. Are you ready? Hey, the population proportion of students who said yes, they want to live on campus housing is 0.72. The sample size was 30. Let me repeat that. We got 0.72, sample size was 30, and the question says, what's the probability that we could have walked in and created a disaster by reporting such a low, from our sample, such a low proportion of, let's say, 0.65 or less. 0.65 or less. That's what that arrow means, or less. That would be a disaster. Our housing director, then we said, hey, I know we said 65% or something less. Let's say we went into the meeting and said 60%, 65% or less, but really it's 72%. So you need to prepare for 648 freshmen coming in to live in the dorms, as well as you got returning sophomores, maybe some juniors still, but brand new freshmen, 648 coming in. Wait a minute, at that meeting you said 65%, I'm only preparing for like 590 or something like that. I was not ready for this additional 60 or however many calculates out to. What's the odds of that happening to us? Are you ready? Here's the information. Let's start out by, I want to make sure we can set this up manually. This is a problem just like this. What number's on the left at the top in your opinion?
0.65.
That's right, the 0.65. What you have to find the probability of, 0.65 or less, minus the given proportion. We all know that's the 0.72. Now, here's the weird part of the denominator. 0.72 times 1 minus 0.72, parentheses, divided by, what's our sample size?
30.
30, but square root, make sure that square root's over the whole denominator. There's the setup. There's most of the points right there with 3 numbers. Now let's do it. Let's do a norm. S distribution equals 1 minus or just norm?
Norm, just norm.
Just norm because it's 65% or less. NORM dot DIST parentheses.
0.65.
0.65 is our first number because the question's all about 65% or less. 0.65, second number.
0.72.
72. Now, here we go. I'm not calculating that standard error of the proportion and then putting just a number there and showing my work. I like putting the whole standard error of the proportion there because that way we're not rounding and we will get an exact answer instead of letting a human rounding take place. So here it is. I'm going to put it just like this is. I'm putting this like on a test or on the homework for part B's. I'm doing the whole thing just like it is right there. Boom to boom, the square root. Here we go. S Q R T parentheses 0.72 asterisk. You gotta have the asterisk. I promise you're losing points. Parentheses 1 minus 0.72 parentheses divide by symbol. That's for Valerie. Okay. I've had sample size. Thank you. 30. But we're square rooting the whole thing, so you need another parenthesis, comma, 1 on the end, because it's normal distribution.
Wait, why do you have to have the asterisk?
Because it will, if you put these two next to each other, Excel does not know to multiply. It will not know without that asterisk. That's the only way to let it know you want to multiply there. You've got to have the parentheses the right spot for order of operations also. Look at this. We could do our homework. We don't even need Thursday's recording. Everybody remember, there's no face-to-face Thursday. Do not show up here Thursday. I'll feel bad. There's no cookies, nothing. All right, where are we at? Is that it? That's not it. We're going to talk more about the central limit there.
Yeah.
Where is it? Hang on, I forgot where it is.
Next Tuesday.
Slide 23, if you got part B. Here it is again. This is the most important thing you're learning today. We talked about it already, but I'm talking about it again. This is what statistics is all about. This is what we've been building up to. Is everything we've been doing has been all about this central limit theorem. It's all about learning about how we can take sampling and know things about the population because of the sample, because of this central limit theorem working. It says no matter what kind of population you have, and look at, we could have, what is that? That's a uniform population. This one is exponential population. No matter what kind of population you have, if you do sampling correctly, you will be forming a normal distribution around a central number, whether it be a proportion or a mean, around a number. It creates a bell curve, and the bigger the sample, the tighter the bell curve is to whatever that mean is. it doesn't matter what kind of data you have in the population, it creates a normal distribution bell curve over the mean. If you're working with the mean, or proportion, let's look at proportions. Or puts a bell curve over the average proportion. Just like that, no matter what kind of particular population you have. But for this to work, you have certain rules. I'm gonna repeat them. As a general guideline, when you're doing central limit theorem with a sample mean, this is mean, not proportion, mean. The rule is the sample size must be greater than equal to 30. Sample size greater than equal to 30 if we're talking about the mean. If we're talking about the proportion for the central limit theorem to work, everything we've been doing here to make assumptions about the population, then you gotta do this calculation for the central limit theorem. And by the way, nowhere on the final exam am I gonna be asking you to do these calculations to determine whether the central limit theorem would work here or not. This is more or less for some multiple choice questions you're getting. And for sure related to the central limit theorem. That's how important this is. For the central limit theorem to work, this sampling to infer things about the population, if you have a proportion involved, both of these have to become true. The sample size times the proportion expected has to be greater than equal to 5, and the sample size times the opposite of the proportion expected, the 1 minus it, has to also be greater than 5. Let's use, remember how many applications we had in our admissions office that we have accepted? I think it was 900, wasn't it?
900.
900. So someone get a calculator out. You ready? Our sample size was 30, I think, is that correct? So 30. So, and our expected proportion, we got it back here, was, the population proportion of those who said, yes, I want to live in the dorm is 72%, right? So here we go. I'm going to take 30 times 0.72 and ask the question, is it greater than or equal to 5? There's the first one. Someone take 30 times 0.72. The other one is 30 times 1 minus 0.72. And I'm asking the question, if that's greater than 5, you said this is, what's that?
21.6.
21.6 on this one down here. 30 times 0.28?
8.4.
8.4?
Yeah.
8.4. Are they both over 5?
Yeah.
So we can apply the central limit theorem, what we learned about our sample, to the population because we met the qualification. So we went to the meeting and said, hey, we think 68%. Our sample says 68%. But there was a small chance, matter of fact, there was a small chance of us blowing it with a sample size of 30. And let's calculate what that chance is. Don't forget, we're calculating right now what the chance is that randomness could have caused us walking into that meeting, reporting 65 or less, putting the housing director in stressful situation once we find out it really was 72. So let's get that answer right now. What is the chances of that? Equals NORM dot DIST 0.65 or less would be awful. 0.72 was the population proportion. Here's our standard error. Here we go, I gotta look at it. Square root, here we go. SQRT, parenthesis, 0.72. Are we on it? Everybody see it? Okay.
Yes.
Times, where's my asterisk? Times, parenthesis, 1 minus 0.72, parenthesis, divide by symbol, sample size is 30, ending parenthesis, comma, 1, parenthesis. Did it work? Did I do anything wrong?
No, it worked. I got 1965.
Point,
1965.
0.1965?
Yeah.
0.1965, so there is 0.1966, quit rounding wrong. 0.1966 chance of randomness causing us to go into that meeting and possibly reporting something bad and putting the housing director in a stressful situation. Here's what you do. You say, okay, what could I do to have walked into that meeting with better information to take less of a chance of reporting something bad? Well, what you have control over is the sample size. So if I, instead of 30, let's say I would have made that 50. It should make it a less chance of us going in there and ruining the situation with the housing director. Sure enough, it brought it down to, what was it before?
19.
19 something, now it's 13 and a half. So now it's only 13 and a half. I'm not happy with that. I want there to be less than a 10% chance, so I'm gonna take my sample size, I'm gonna do 60. Oh, so close.
80.
That's an overkill. I'm doing 70. There we go. I'm gonna have to do a sample size of 70 so I can walk in that meeting with a 90.4% chance, a 90.4% chance that I'm reporting something that's gonna be like the population. There's still a small chance I could be reporting something bad. That happens with randomness, but odds are hugely in my favor, and I like these odds, 90% chance of them being in my favor that I'm reporting something good to the thing. Don't forget though, we could be reporting too high, it goes the other direction. We'll talk about that next week actually. So, how do we feel? Can we understand central limit theorem and what the rules are to central limit theorem and how it works? Okay, let me look at my notes. We got deadlines. I only have a life lesson. I'm gonna turn off the thing for life lesson. Hang on, I only have one life lesson before we go. It's early. Any questions? Any questions? Again, if you came in late, grab something on your way out. I got some stuff for you.